Hello everyone. So today I'm going to start this Rouche's theorem, which is very important, and we should know about the argument principle and its lemma for this theorem, right? So let's start. Rouche's theorem states that suppose fz and gz are analytic inside and on a simple closed contour C with mod of gz strictly less than mod of fz on C, then fz plus gz has the same number of zeros as fz inside C. That means we have to prove that number of zeros of fz is equal to number of zeros of fz plus gz, right? To prove this theorem, we need the lemma, which I have proved in the previous video. And what the lemma was, I'm also stating this lemma here with proof again for you all. Suppose fz and gz are analytic inside and on a simple closed contour C with fz and gz having no zeros on C, then delta C argument of their product is equal to delta C argument fz plus delta C argument gz. That means the variation of arguments in their sum. So you have to prove this lemma first. I am stating the proof. Let number of zeros of fz equal to n1, number of zeros of gz is equal to n2. So by argument principle, we apply this principle on fz, we get 1 over 2 pi delta C argument fz equal to n1, and then applying this principle for gz, we get 1 over 2 pi delta C argument gz is equal to n2. Now, because the number of zeros of fz into gz, their product, that is equal to n1 plus n2. This I have explained why this is equal to n1 plus n2. So again by argument principle, which is applied on the product, 1 over 2 pi delta C argument fz into gz is equal to the number of zeros, that is n1 plus n2. Now put the values of n1 and n2 over here and cancel this 1 over 2 pi on both the sides. You will get the result delta C argument fz gz is equal to delta C argument fz plus delta C argument gz. This result I need to use in the main proof of the theorem. So to use this result, you have to prove this result first before proving the main result of the theorem, right? Now, what argument principle need that is the functions fz and gz. These should not vanish on the boundary, which means these have no zeros on the boundary. Then only we can apply the argument principle. So for the proof of the theorem, we should have to prove first that the functions which are given, what are the functions given to us? Fz and fz plus gz. This is one function and this is another function, fz plus gz. We have to prove first, we have to claim first that both these functions cannot vanish on the boundary C, right? So neither fz nor fz plus gz can vanish on the boundary C. This you have to prove first. So if possible, suppose for some point A on C, we have this function to be equal to 0. This function vanishes at point A. So fz vanishing at the point A means you are saying that f of A is equal to 0, right? And also in the Rouche's theorem, we are given that mod of gz is strictly less than mod of fz. It is given to us, which means what we are saying that mod of ga is strictly less than mod of fa, but mod of fa is equal to 0, which means mod of ga is equal to 0, which cannot be is less than 0, which cannot be possible. Why? Because mod is a positive quantity, right? So mod of ga cannot be less than 0 because it is a mod, of course. So this is not possible. So which is not possible. That means the function fz is not vanishing on the boundary C, right? Now check for the other one, fz plus gz, right? Put the point A in place of z. Let's check, is this function vanishing or not? Now f of a plus g of a, if this is equal to 0, which means what we are saying that then f of a is equal to minus g of a, which means mod of fa is equal to mod of ga, which is again a contradiction to the fact that mod of gz is strictly less than mod of fz, right? So this is again a contradiction to our fact, which is contradiction to the fact that mod of gz less than mod of fz on C. So thus neither fz nor fz plus gz can vanish on C, right? This thing clear? This has been proved now. Now we can apply the argument principle. For that we have to choose the number of zeros we have to suppose. So let number of zeros of fz plus gz is taken to be capital N and number of zeros of fz is taken to be capital M. Now since fz and fz plus gz are analytic inside and on C and also have no zeros on C, which we have just now proved. So now we apply the argument principle on fz and fz plus gz. Now for fz we have 1 over 2 pi delta C argument of fz. This is equal to, what are the number of zeros for fz? Capital M. And 1 over 2 pi delta C argument for fz plus gz. This is equal to the number of zeros of fz plus gz, which is equal to n, right? Now I have to prove n minus m to be equal to 0, right? This we need to prove in Rouche's theorem, that both the functions are having the same number of zeros. That means we have to prove that n is equal to m. So I have to claim that n minus m to be equal to 0 first. So claim n minus m to be equal to 0. This we need to prove. So for that, I'm checking the value n minus m equal to, put the value of n here, I get 1 over 2 pi delta C argument of fz plus gz minus, put the value of m, 1 over 2 pi delta C argument of fz. Clear? Now taking this 1 over 2 pi common, 1 over 2 pi delta C argument of fz plus gz minus delta C argument of fz (1 over 2 pi). Now I'm taking this fz also common here. Delta C argument of fz into 1 plus gz over fz minus delta C argument of fz. Now here I have to use that lemma, that is the variation in the argument for the product of the function is equal to variation in their arguments of their sum. Now here I am having the product, this fz with the product 1 plus gz over fz. I have to apply that lemma here, which gives me, so this will be equal to delta C argument of fz. Now product will be changing to first delta c argument of z, then plus delta c argument of 1 plus gz over fz, then remaining minus delta c argument of fz. We have used the lemma. In bracket I am writing using lemma. So this is equal to, now first term will be cancelled out with the third term. So we are left up with delta c argument of 1 plus gz over fz. Right? Now required to prove that this argument is, 1 over 2 pi is also there. So required to prove that this argument, delta c argument 1 plus gz over fz to be equal to 0. This we need to prove now because we need n minus m to be equal to 0. Now since mod of gz is strictly less than mod of fz on c, right? So let's take this 1 plus gz over fz to be as a point w. So I take this point w as 1 plus gz over fz, which is always lies inside the circle mod of z minus 1 is equal to 1. Now this circle means I am having the radius 1, and also this circle is centered at 1 with unit radius. So let's draw the circle and check whether this point lies inside the circle or not. So this point always lies in this circle. Let's check. This is your x-axis, this is your y-axis, this is your point 1, and this I have drawn a circle with unit radius. Now I'm having the circle mod of z minus 1 is equal to 1. Now to check this w lies inside the circle, we need to see that mod of w minus 1 should be less than 1. So I should place the value of z to be w, and I should check that this mod w minus 1 should be less than 1. Is this is less than 1 or not? If this mod is less than 1, which means this w is lying inside the circle, right? So let's check the mod w minus 1 is equal to, what is w? This is 1 plus gz over fz minus 1. 1 cancel, you get gz over fz. According to the condition that mod of gz is strictly less than mod of fz, so this ratio of the mod is always less than 1. Because it is given that mod of gz is strictly less than mod of fz. So if you take this mod of fz to be in the denominator of mod of gz, you get this mod to be less than 1, which means mod of w minus 1 is proved. This mod of w minus 1 is less than 1, which means this w point lies inside the circle. Clear? Alright. Now do you notice that this w lies in the right half of the plane? This is your xy plane and this w lies in the right half of the plane. Yes. And suppose this is your pi by 2 and this is your minus pi by 2. Because we are talking about the arguments, so this angle will be pi by 2 and this is minus pi by 2. Right? So if w lies inside the circle and also in the right half of the plane, which means if we check the argument of w, this argument of w, that is the angle, this lies between pi by 2 and minus pi by 2. Yes, which means what is the meaning of this statement? That argument w lies between pi by 2 and minus pi by 2, which means the net change in argument w, that is a variation. This change is equal to 0 when z traverses c, which means the variation in argument of w is equal to 0, which implies the w is nothing but 1 plus gz over fz. We have taken w to be equal to 1 plus gz over fz. So we are saying that delta c argument w equal to 0 means delta c argument 1 plus gz over fz is equal to 0. So mark this as your 2. We have marked this as 1. So if I put the value of 2 in 1, I will get this whole thing to be equal to 0. Okay, so I'm putting this value 2 in 1. So from 1 and 2 I get n minus m is equal to 1 over 2 pi 0, which is equal to 0, which implies n is equal to m. Thus, we have proved that what is n? The number of zeros of fz and of fz plus gz, which is equal to m, that is the number of zeros of fz. So fz plus gz has the same number of zeros as fz inside C. Result is proved. Okay, just keep in mind a small remark that in Rouche's theorem, the condition mod gz is strictly less than mod fz on C, right? It cannot be relaxed to mod gz less than equal to mod fz. You cannot take their mods to be equal. So mod of gz should always be strictly less than mod of fz, right? This you have to keep in mind. So hence here ends up the proof. In the next video, I will be doing some exercises based on this Rouche's theorem, which are also very important. So thank you for watching this video. We have to meet with examples and assignments for this Rouche's theorem in the next video. Thank you. Goodbye. Have a blessed day.